So let's get started on particle physics. This is the plan. Let's take a look first at the Yukawa particle and the Heisenberg uncertainty principle revisited. Now, we've seen this before, and it's something that I meant. A number of the things in here are actually a review from some of the stuff that I've covered in the past. So, but that's okay. It's okay. All right, we talked about nuclear forces, the fact that you have a proton that is made out of quarks, 3 quarks for muster mark, was taken from Finnegan's Wake, and that's where the name quark came from. It was coined by, what was the guy's name? Murray Gell-Mann. He needed to come up with a way of accounting for the things that were observed in particle accelerators. So you have a particle accelerator, you smash, I guess we'll draw that picture. Here's your particle accelerator, it looks like this. It shoots particles in some direction, and you smash it against a target. In this case, it was fixed target experiments. That was what was run back in the day. And there are a variety of different kinds of particle accelerators. The early ones were cyclotrons, which we'll also talk about. Anyways, you produce a bunch of particles that come out, and you have detectors out here that tell you what those particles are and what some of their properties are. You can measure, for example, the charge to mass ratio, Q over M. So the way that you do that is you have a magnetic field here. So here's a magnet, and charged particles will spiral in one direction or another depending upon whether they're positively charged or negatively charged. If you have a low mass particles are easy to push around. So that would be a low mass particle would be a large charge to mass ratio, right? M is small, therefore the ratio Q over M is big. And so those ones, because they're easy to push around, will spiral in tight spirals, where if you have a larger mass particle, then Q over M is a lot smaller, and you'll get a path that it's still curved, but it curves with a larger radius of curvature. So you can use these tracks to determine the ratio of the charge to mass, and since there are probably other ways to diagnose the amount of charge that an object has. Typically, if it's an elementary particle, it will be have a charge of 1 or -1, but there are particles that have charges of -2, and I think -2 is about the best that you can do with elementary particles. Anyways, or they're not elementary particles, but with the hadrons. So hadrons are particles that are made out of 3 quarks. The best you can do is have 2 minuses. So this is, these were the things that were measured. You can measure the masses of the things and the properties that they might have and the different kinds of decay processes that we'll go through, because you'll get some vertex will come along like this, like you'll have a vertex and then this thing will disappear. So here's the track in your particle detector. You have these 2 tracks coming out off of a vertex that we know is coming from some direction. This one might curve in some direction that tells you that it has some charge. This one is going to be going straight, and then it might disappear, and then it will appear again with something that looks like this. And so you'd say, oh, well, this thing, it split, and then here's a particle that came away, and then there was some neutral particle that appeared right here, and then that decayed and produced an electron-positron pair. So these are the kinds of vertices or kinds of tracks that will appear in your detector, and you can use them to infer the properties of the different particles that are involved in the interaction. So we'll take a look at that real quick. If I looked at tracks, particle physics tracks from some detector. Go with images and we'll see what we can come up with here. Yeah, so something like this. So this is an early image. They don't typically look like this quite as much anymore. So you can see, like, for example, right here, there's this vertex that appeared out of nowhere. So it was a chargeless particle that came in, decayed into 2 particles like that. You can see this spiral, some particle coming with some energy like this. If they turn the opposite direction, then then the sign of the charge is different. You might have like protons streaming through or whatever. Anyway, so there's a variety of different ways, or a variety of different interactions that appear in these kinds of, in this case, it's photographic film. Modern detectors don't look like this, right? They have different kinds of detectors that they use. Anyway, so that you can determine all sorts of different things, and you can show that electric charge is conserved and that mass or energy is conserved. You can show a variety of things, including a number of other quantities that are conserved, such as strangeness, Well, that's not the right thing. Strangeness. So this was the first quark that was discovered, was the strange quark. It's the next most massive quark after the up and down quark. And so strangeness, this was something that came up in early particle detectors, and they're like, that's kind of strange. I don't know what it is, but it seems to be a quantity that's conserved in some interactions and not conserved in other interactions. And over time, through the course of the 40s and 50s and early 60s, there were a variety of other particles that were discovered. So several different kinds of particles were found, the J psi particle, and et cetera, and so forth, lots of these things. But there wasn't really a way to, so the J psi particle it was called the J by one accelerator and the psi by another accelerator, and they basically discovered the particle at the same time, and so they called it the J psi. It's not named after Dr. Strange. That is true. The strange quark is not named after Dr. Strange. Is there a limit to how much energy a particle has? No, you can have particles with basically an infinite amount of energy. So there you go. There's a limit to how much energy a particle can have that we can create on the Earth. Right now, the maximum energy that we can get is about 14 TeV on the Earth that we can produce in our laboratory. In terms of particles that are coming from space, so cosmic rays, then you're looking at probably something like 1 eeV, an exa electron volt, which is what I think that's like 10 to the 18 eV, where a TeV is like 10 to the 12. So this would be 10 to the 13 electron volts. Okay, so all these particles were discovered, but there wasn't a good way to catalog them. We didn't have the equivalent of the periodic table to tell us, oh, here's what we're looking at, and we should expect particles in this area. As the periodic table was developed, it was like, here are a bunch of chemical elements, and these ones all have similar properties, and these ones have similar properties, and there isn't one that's right here. Like this one was missing. And so it was a prediction that, oh, there should be an element that we can find that has properties similar to iridium, but that just hasn't been discovered yet. So the periodic table is a way of organizing stuff, organizing the chemical discoveries or the discoveries of different chemical elements in order to determine, what's actually happening in the structure of the atom. Well, going on here with these particles, there wasn't a periodic table. There was just this particle zoo, a large collection of particles that had been discovered, the omega, the cascade, the sigma particle, the rho particle, the pion, and there wasn't a way of showing how they related to each other, other than that sometimes this one would decay into that one, and sometimes it would decay into this one, and then you get electrons. And this is where Murray Gell-Mann comes into play, and he said, oh, okay, maybe this might not be right, but let's pretend for a moment that some of these particles are made out of quarks, and some of them are not made out of quarks. And those quarks come in 3 different varieties, and they call them up, down, and strange varieties. Up, down, and strange. So, and then he said, I can come up with a way of tabulating or assigning these characters to these different particles that matches their properties, or at least keeps track of their properties correctly. So for example, if I make a dud, DUD, we can call this the neutron. It has the properties of the neutron. It has the right electric properties of the neutron. It has the right mass for the neutron, and so forth. And then if I had an up, up, down, so down, up, down, or down, down, up is a neutron. Up, up, down would be a proton. And then what if I had a down, 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 or an up, up, up? That these would be other particles that we found. I don't remember which ones are which, like the rho and the K. We'll look it up and see what they are. Anyways, there's particles that had been discovered that needed names that came along like that. There's no left, right, and there's no B or A particle. Okay, there is a B particle, but that's something to come up. But there's no up, up, down, down, left, right, BA. It's just ups and downs and stranges. So the strange quark would be mixed into this. He's like, okay, now we find a strange particle, and what I can make is an up-down strange, for example, and that would correspond to whatever particle it happened to be. Was it a lambda? Well, anyways, we'll look this up and see what it is. But what you should get from this is that there are, with 3 different quarks, up, down, and strange, you can have up, 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 down, 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 strange, 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 and all the mixtures. So this would be what, up, up, down, 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 up, and then over here you'd have up, up, strange, strange, and then you'd have down, strange, strange, and down, down, strange. So these are all separate mixtures of these different things, and you'd have an up, down, strange right here in the middle. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that's 10. So, oh, look at that. I don't fit. Okay, well, anyway, so there's that. That's an interesting phenomenon. Stupid pointer. And now the mouse pointer isn't even on the screen. Those are the 10 particles that were predicted from this quark model. That's what I wanted to do, was like that, to make it so that all these things were visible. All right, let's see what those things are called. So this was Gell-Mann. He comes up with this bookkeeping mechanism, like how do I keep track of all these different particles? And so if I do this, then these are the different combinations that I can get. And he was able to assign those different particles to ones that had already been detected, except for one. This one right here, he's like, there should be a particle that has these properties, the properties of 3 strange quarks and whatever the charges are. I think it's 2 negative charges. So if I look at the okay. So there was one thing that I was missing from that, and that is that there are different ways of arranging these spins. So I did point out that these ones, these delta ones here, that should be the neutron and proton. However, it's related, the difference between the neutron and proton and these delta particles are the way that their spins are oriented. So in particular, if you have 3 quarks, you can have 2 quarks you can have all 3 quarks pointed in the same direction, or you can have 2 quarks pointed in one direction and 1 quark pointed in the opposite direction. So each of these particles, each quark has a spin, and you can have 3 spin up, or you can have 2 spin up and 1 spin down, or the opposite of that, right? You can have 3 spins down and 2 spins down and 1 spin up, but these are the only 2 basic options. If they're all spin down, then that's essentially just a reflection of it. Okay, there's no, and so you're going to have an ensemble of particles that you put together with this set of spins, and an ensemble of particles that you put together with this set of spins. So this set that I just drew here, uglily, this set right here, this triangle, is when all of the spins are oriented up in the same direction like that. That's an excited state, because in general, the particles will try to align themselves or anti-align their spins. Like the lowest energy state will be with their spins anti-aligned. Okay, and when you have spins that are anti-aligned, there's also another set of possibilities where when you add the wave functions together, there's going to be like a singlet state and a multiplet state where there's a minus sign separating the 2 parts. So you could have a quantum state where it's like up plus down, or you can have up minus down. And so this has certain spin properties and this has different spin properties. So there's different subtleties to these diagrams that are important to the practitioner, but aren't really that important for our discussion. What level is this course? High school. This is a high school course. We're looking at AP Physics, but we're looking at it in a little bit more depth than you might normally get in an AP Physics class. So the stuff that we're covering here would be addressed in an undergraduate level particle physics course. All right, so these are the spin states where all the spins are aligned. So this delta minus, delta naught, delta plus, delta plus plus. And you can see when you rearrange these quarks, so going from this row, so this is the top row on this diagram. So this diagram here, this top row here, that is this row right here. And then we're moving, as we move down and to the right, like this, that's moving down on this graph. So this actually predicted the presence of this omega particle right here. So this omega particle had not been observed, and it was predicted to have a certain amount of electric charge and a certain mass. And that basically is what won Gell-Mann the prize, is he predicted the presence of this particle, and it was found, and that confirmed at least the bookkeeping mechanism, whether the quarks were real or not, is a separate discovery. But the fact that the bookkeeping method to keep track of what all these different particles are worked out was a pretty big deal. And it explained all of these particles that had been discovered, right? So we have something like a dozen different particles that had been discovered, but had not been, they weren't predicted from the standard model of just atomic physics where you have a nucleus of protons and neutrons. So these were definitely new particles to be observed. The relationship between those particles wasn't understood until Gell-Mann came and explained it. All right, so you have this baryon decaplet here. These are ones where all the spin states are oriented in the same direction. Notice that the delta particles themselves, there's nothing special about them, but these ones here, the sigma and the cascade, notice that there's a star by each of them. So maybe I'll zoom in a little bit more so that you can see this star. Okay, so that star means it's an excited state. So there's an excited state here, an excited state there. And when it goes to the ground state version of that, then it shows up in this plot right here. So the sigma minus, sigma naught, and sigma plus. Sigma minus excited, sigma plus excited, and sigma naught excited. So these delta particles are actually kind of like neutrons and protons, but they're also in an excited state. You also have here this lambda particle. That's one where you have the spin states aligned in a slightly different way. So anyways, these are the predictions, these different types of particles, different arrangements of these quarks that were made by Gell-Mann. Another way to do it is with this Meson octet. So these are particles that are put together with a quark and an antiquark. So a quark and an antiquark, there are basically 4 different brands. This K naught, K plus, K minus, and K naught bar. So these are opposite and diagonal. These are pairs of quarks. And so instead of triplets of quarks, these are pairs of quarks, and it's actually a quark and an antiquark. And a pion those are the important ones, the pions. And then there's this eta particle that is the eta particle is the difference between a quark plus a quark and a quark minus a quark. It'd be like 1 over root 2. The quantum wave function would be something like this, 1 over root 2 times that, and 1 over root 2 times this. The fact that this has a minus sign in it implies things about the spin properties of it, and that's encapsulated by having these as 2 separate particles. So this is the prediction from Gell-Mann that particles should arrange themselves like this. He made the prediction that this should exist, and lo and behold, it did. Well, time goes by, and there were other quarks that were discovered. So the strange quark was the first one discovered, but then along came a charm quark. So you add the charm quark to the mix, and now you have, instead of a triangle, you have a tetrahedron. And you can have charm, up, down, strange, and you can put together any combination of all these particles. So you have this triangle here, and then if you add 1 charm quark, then you get a different combination of possible particles, 1 charm quark plus any mixture of these up, down, and strange quarks. And then 2 charm quarks, and you get the same property, or the same ensemble of possible combinations, and then you have a particle that's 3 charm quarks. Okay, and that showed up in this one right here. So this is a diagram. That shows what happens when you have up, down, strange, and charm quarks all in the same mixture. Okay, so you can see the protons and neutrons that are down here, the cascade particles that I mentioned, and then you've got down, down, charm, down, strange, charm. And the names are actually, they kept them as like the cascade and the sigma particles and stuff like that, but they added the subscripts to describe what the quark composition is of these different things. Okay, so these all describe the different quarks that go into making these particles up. And for a long time, so through the 1980s, particle physics was geared towards discovering what are these different particles, what are the properties when you mix quarks together in these certain varieties. Okay, and the way that those were discovered were using particle accelerators. So if we look at early particle accelerators, that would be like the cyclotron. The idea of a cyclotron is you have an alternating electric field and a magnetic field. Okay, let's see. This is, where's a good picture? This is probably the best example of a picture. So you have these two, they're called Ds. So here's these two Ds, they're separated from each other, and then you run an electric field across this part in the vertical direction. So the electric field runs up and down like this. You squirt in some particles that are charged, and there's a magnetic field. So the magnetic field is pointing towards you, like through the screen directly towards you. Let me draw a picture of that. So we have, here's your cyclotron, like this. Okay, it's got this diameter, or it's got this slice cut out of it. Here's your three-dimensional version of it. It looks kind of like that. You'll have a magnetic field going like this through the system. The magnetic field takes the charged particles and causes them to move in a circle. So then you have an electric field that moves across this diameter. I'm sorry, not across the diameter. It moves across the gap in between the two halves. And it will oscillate, pointing this direction and then pointing that direction, and then pointing this direction and pointing that direction. And you time those oscillations so that the following thing happens. So you squirt in your particles, they're accelerated this way, and then they hit this edge of the electric field. The magnetic field causes them to curl around. So now they curl like that, and then they hit this side. By the time they hit this gap again, by the time those charged particles have curled around and hit the gap, the electric field has switched directions, and now the particles get accelerated the opposite direction. So now they're moving faster. And as they move faster, they're going to create a larger, because they're moving faster, they're going to make a larger circle. And then they curl around because, again, the magnetic field is there. So the magnetic field is static. The electric field is oscillating back and forth. So that by the time it gets back here again, it gets accelerated across this gap, and it continues to make a larger and larger circle, and then eventually escapes out like this. And that's where you put your target. Okay, so that is what a cyclotron does. You have the magnetic field, and then the particles will move in an ever-expanding circle until eventually they escape, and you can direct them wherever they need to be directed. Now, there were a variety of different kinds of particle accelerators. Initially, they were using cyclotrons, and then as they got to more and more like high-energy particles, they had to come up with different types of accelerators. So I'll give you a few examples. So there's Caesar at Cornell. I think this is turned off now. The Cornell Electron Storage Ring. 40 feet beneath the alumni field on the Cornell University campus is the 768 meter Cornell Electron Storage Ring, constructed as an electron-positron collider operating at the center of mass of 3.5 to 12 GeV. Caesar is now used as an X-ray source. Okay, so they use it as an X-ray source. The way that it works is underneath this building, you had a couple detector bays and things like that. Not underneath the building, underneath the campus, you had these couple detector bays, and then this tunnel that would go around, and you would send, in this case, it was an electron-positron ring, so they would send electrons in one direction around the ring and positrons in the opposite direction around the ring, and get them to collide at the other end. So you add energy to the particles as they come around. When they collide, then you get MC squared worth of energy, well, gamma MC squared. So you accelerate them around, they have lots of energy that is from our relativity part. Oh my gosh, what the heck? I want the pen. You get gamma MC squared. That's the total energy that you have for one of those particles. And then you can use all this energy to make, whatever particles you want. So like the protons, or you could make a cascade particle. All of these things from this energy that's been built up by accelerating the particles around. So you add energy to the system, you get them to collide with each other, and then through a variety of interactions that can take place, you'll produce a shower of particles that come out of it. I don't know if you can walk through the tunnels of this at this point, but it's there. The fact that they use it as an X-ray source is for the following reasons. When you take an electron, so here's an electron, and you accelerate electron in a circle, it's going to give off radiation all along as it goes. So you have an electron traveling in a circle like this. That circle will actually decay as it loses energy. Is it gonna? Yeah, so that's what's gonna happen. It's gonna decay as it loses energy. So we saw that from that bubble chamber image. if I still have it, particle physics track. So the reason that these things are decaying is because they're giving off radiation. They give off radiation because as they accelerate, as they accelerate, they give off radiation that comes off tangent to their motion. Okay, that's called synchrotron radiation. And so they're losing energy, and because they're losing energy, they spiral inwards, and then they basically stop moving. So that's why these particle tracks, oh my gosh, here we go. These particle tracks have this curl, they curl in and they spiral inwards. I guess those are the same thing. I'm doing so well today. They spiral inwards like that because they're losing energy in this fashion. So this is called synchrotron radiation. So with these particle accelerators, if you want to get particles going fast enough, then you have to overcome the fact that the electrons are going to be losing energy as they go because of synchrotron radiation. And so you have to make the radius of curvature really large. You have to have lots of magnets and things like that to direct them around. And there's a limit to how fast you can get them moving, because as you add more energy to the system, they're just going to radiate that energy away. So that limits the maximum energy you can get for the electrons in that system. What it does do in addition to that is that you could put experimental bays like this around the perimeter, and as the electrons are moving around, you take this radiation that comes off the side and you use it to run other experiments. So these radiation that comes off here is usually X-rays, and so this is an X-ray source. You can use it as a particle collider if you can keep enough energy added to the system, and you send the electrons in one direction and the positrons in another direction and have them collide. You know, they'll collide over here and make a big explosion with all these particles that come out. But then once this becomes obsolete, and I'll describe the reason it becomes obsolete is because you're limited in how fast you can get them going because of the fact that they lose energy every time they go around. And then they just said, okay, well, we're done. We're not cutting edge anymore as a facility to do electron-positron collisions. However, we are still good at producing X-rays. And so you'll do X-ray physics, so condensed matter physics, looking at crystal structures and things like that, by having experimental bays that come off the sides. Let's see, is that what Fermilab was doing? I will show you. So Fermilab doing their radiation treatments or medical treatments was different, because in that case, they were just picking off protons that were coming out of the beam. So they already had a beam of protons and they were just deflecting some of those protons into the medical facility. In this case, these are X-rays that are produced, high energy X-rays that are produced from these synchrotrons. Okay, so Caesar, we'll come back to it here, is this ring. And you can see the synchrotron, you can see where they have the LINAC. So the LINAC is where they accelerate the particles to begin with. Let me see this image. So they have this gun, produces electron-positron pairs, or produces electrons, it's an initial linear accelerator that accelerates something. It hits a target, so this is probably the target, and then it produces electron-positron pairs. You can select the electrons and positrons that you want by having a magnetic field of the right strength, given how fast the particles are moving out of the system. You have these magnets that will steer the electrons and positrons with some radius of curvature, and the protons will have a different radius of curvature that's much larger. And so you can make it so that the electrons fit into the tunnel, that they turn at the right radius to fit into the tunnel, and the protons and antiprotons and other charged particles don't. They, hit some slab of concrete or something like that. So you direct the electrons and positrons into the synchrotron ring, and it goes around, and then it says that they have these transfer lines. So as the bunches of particles are moving around, then you can have them branch off and come into this, I guess in this case it's a storage ring that they're using for the different detectors out here. But then you can divert them so that the particles come into some other ring and then slam into each other at the other end. So this is for a synchrotron type beam. And the fact that this is an electron-positron beam is marginally important. Anyways, it's limited in its ability to do stuff because of the fact that the electrons are always moving in a curved path and they always lose energy. So what came after this was a linear collider. So SLAC, the Stanford Linear Accelerator Center, is here on the campus of Stanford University. This is SLAC. Okay, so this line, let's see if we can look at it on a satellite image. Start here, and it accelerates along this line. And the reason that they have it moving in a straight line is because now it's not losing energy. You can just accelerate in some direction. It's not losing radiation off to the sides and limiting your ability to go to high energies. Then what happens is down here, they have a bunch of buildings that are fixed target buildings. So it gets to some switchyard type place where they have magnets where they can direct the beam to go in some direction. You don't want to have a large deflection, because the larger the deflection becomes, the more energy you lose in that deflection. And so it comes in here, it switches from in some building that's in around this area, and gets directed into these experimental halls that are pointed towards that vertex. And then these experimental halls, you'll put up, whatever kind of fixed target you want to have. So this would be a slab of lead or something like that. The electron would come in and hit it, produce a bunch of particles that come out, and then you can do your high energy physics studies looking at these different branches. The last major accelerator that they built at SLAC was called, I think it was called Babar. And that was back here. And what happened there is that it would come out, the beam would come out, and then it was directed this way. So I don't know if these are the buildings that were part of that experiment, or if it's this berm that's behind it. So I'm not totally sure where it's located. But the beam would come in, and it would come around, and then they would curl it in and get a head-on collision between, so the two beams would come out, and then they would come around and hit behind it. And that was the last set of experiments that they did, and that was around 2000. And now they just use it as a synchrotron source. Notice that they also have some circular synchrotron type buildings in these different places as well. So there's all sorts of stuff that's going on at SLAC. They don't do as much. It's not high energy physics the same way that it used to be, but this was cutting edge as a electron positron collider. Let's take a look real quick at Babar experiment. There's also Bell. Okay, so here's Babar. That's what it looked like. Let's see if we can see the image of what the accelerator complex looked like. Open in new tab. Okay, so this is the main line, and then it was ejected out here and was sent around, and the collision happened back here. Another one was called Bell. I don't know if this was at the same place or not. Okay, so that was at Japan, at Keck. Anyway, so these are electron-positron colliders. And they're a linear collider where most of the acceleration happens in a straight line instead of in a circle. Now, when you are done with, so you're limited what you can do with electrons like this. And so if you had a heavier particle, it would lose less energy as it goes around. So instead of using electrons, if you use protons, then protons are 200 times more massive. And so you can get, 2,000 times more massive. So you can get them accelerating with more energy, but they don't lose as much to the radiation because a lot of that energy comes from their mass, right? You already have a boost of a factor of 2,000 in their energy, even if they're moving at the same speed. And so they'll be moving at the same speed with 2,000 times as much energy, which means you can have an accelerator that produces collisions with 2,000 times as much energy, but loses 1/2000th of the energy to radiation because they're moving more slowly, and therefore they're accelerating more slowly. And the amount of synchrotron radiation you produce is related to the acceleration of the particle. Okay, so this is where you have the Hadron colliders. So what we've seen so far are electron colliders or lepton colliders. And Fermilab is a Hadron collider. It's a proton antiproton collider. Let me go. Okay, so this is the map. Let's go to the maps. Okay, now Fermilab isn't operating anymore. We'll go to CERN in a minute. I should say the main part of Fermilab is no longer operational, and that's this part. Okay, so this is the main ring. It's a 1 kilometer radius accelerator. It was designed and built in the 1970s. It made a number of early discoveries. I think it discovered the Z quark, or I'm sorry, the Z particle, which is not a quark, but discovered the Z. They discovered the bottom quark. They did a bunch of bottom quark physics. I don't think the bottom was discovered here, although we can look that up. The top quark definitely was discovered here. That was in the 90s. So initially, this was the ring. There was a linear accelerator. It came over here, and then the particles were, so the linear accelerator is on the side of this building. This is the linear accelerator, this berm right here. Came down. It was boosted up in this cyclotron. So there's another cyclotron, except instead of having those D halves, it's just accelerated around with a set of magnets and electric field, between those magnets. So it boosted up to a higher energy here, and then it was injected into you can see the berms where the beam travels, injected into the main ring down here. And the main ring, it circulated that beam of protons in this direction. Hold on, is it in that direction? It must be circulating in the other direction. So it must come out of this booster and sent in this way. Okay, this complex of buildings down here is for the Tevatron. That's a later design. But initially, I guess it went through the booster and it was sent this way up through the ring in this direction. So the reason I say that it must have been going in that direction is because as it came around, then you had detector facilities around the perimeter. So this used to be where CDF is located. They retrofitted this building into a different complex. And then you had, I think that's A0. Oh, A0 is here. This is B0, C0. Then D0 is this set of complexes. This is where they had another detector set up. And then there's, I think, an E and an F0. E0 is over here. Maybe there's not an F0. Anyway, so there's a bunch of buildings around the perimeter that were just had names associated with them. And this is one of the major detectors, and this was the other major detector up here. From this ring, after a number of circulations, they could send it down. They could siphon it off in what's called the Switchyard, which is in this area. So the Switchyard is here. And they could send those beams down into this complex of fixed targets. So these are halls where they would do fixed target experiments. So instead of colliding the beams together, they would hit the fixed targets. Initially, it was just fixed target experiments. So you would circulate the particles around in that loop, and then you would send them out in a straight line and hit the fixed targets. Eventually, with the upgrade, and I'll describe the upgrade, they had counter-propagating beams, and then they would collide the beams together. So these different branches were for different kinds of physics. So on this, notice how they're all kind of pointed back towards this Switchyard. It's similar to the way we saw at SLAC, where all of those buildings were angled so that when the beam was coming in, it would be deflected by a small angle, and then you'd have a series of targets in that particular direction. So in this case, on this side, so there's a straight line that runs down here. Here's that straight line. Okay, and it runs clear back to these buildings out here. They're not used for what they used to be used for. Now they're used for different things. But there used to be particle detectors in all these different areas. This collection of buildings on this side, so the south side of that line, these were the Proton Buildings. So the protons were directed down here, and they would have fixed target experiments designed to look at interactions with protons. There's a really cool building called this one right here. I think it's called the Proton Pagoda. It's the access to the tunnel. Okay, so here's the access to the tunnel. It's this weird looking building, and it has a double helix staircase in it. So it looks kind of like a virus, where you have the head of the virus, and then you have this double helix staircase that goes down into the proton detector. So you can see these two berms. You can see some detector buildings along here where they would have a variety of different targets. And then this was like a control, almost like a control tower. All right, in the middle part, so this is where I think these were the neutrino experiments that ran here, because neutrinos you can't steer. Once you produce a neutrino, it's going in a particular direction. So neutrino buildings or neutrino experiments were lined up along this one. So this is, now it's called the Silicon Detector Facility, SIDET, right here. But this was the holographic bubble chamber. So there was this object here is a big bubble chamber, huge bubble chamber. You can see a car, it's bigger than a car. And it used to be housed in this building over here. And they would fire a beam at it and have a bunch of detectors around the perimeter of this building. And then as the particle came in, it would produce, whatever trail it would produce in the bubble chamber, they would observe it. So that was where this was located. Anyways, there's a bunch of buildings along this line. I don't know if they did neutron experiments. I do know that they did neutrino experiments that ran almost all the way to the edge of the laboratory. Right, so I guess this is the last one there. Some of these buildings are new, some of them are old, and this is one of the older buildings. You can see the power supply coming in right here. These are called pi poles. So the electricity to supply the accelerator came in along these things. They were designed by the first laboratory director, and he had to kind of convince the power company to let him build them like this because they wanted to build them somewhere else, or they wanted to have different pylons that they'd already used in the industry before. Anyway, so that's the beam for neutral particles. And then protons over here, neutral particles here, and then this is the Meson Building. So this is where they would do experiments with mesons, so like pi particles and kaons and things like that would come into this building. And you can see, again, you had this main building with a roofy, leaky roof. It's kind of a weird looking, it's almost like pipes, like they were pipes that were sliced and then piled up to make the roof here. A lot of the roofs leak at Fermilab. It's kind of what happens when you sacrifice function for form. Anyways, from here, there are a bunch of tracks, like trails, and you can have fixed target experiments all along these things. So like you'll have a fixed target here, and then some distance, you want some of the particles to decay away, and so at some distance you place your detector where the noise decays away and you're only left with signal. Anyway, so there's a variety of places to put detectors along these different trails that come in along, whoa, that's not what I meant to do. Come in along this berm. Okay, so this tunnel that runs along here and comes back to the switchyard, which is right here. You can see where all these berms lead. So here's the switchyard. And this is the beam coming out of the Tevatron. So not the Tevatron, the beam coming out of the main ring. So the main ring is right here. And then it would be directed, like there's a thing here that siphons off from the beam, sends it down this way, and then it gets redirected with a series of magnets into the different trails or different possibilities. This is the computing center. It's designed to look like a Cray computer from back in the day. You can see how much that looks like a Cray computer. These things here are helium storage tanks for the Tevatron, which came later. And this is where they assembled the different magnets, and anyways, there's all sorts of stuff that goes on at this location. Okay, so that was the original Fermilab facility, was a main ring. It would accelerate the particles in the ring, and then you would send them off to fixed targets. Eventually, it was found that you could do better, you could get to higher energies if instead of having a particle come in and then slamming into a fixed target, if you had two particles that were going in opposite directions and slammed into each other. Now, there are other particle accelerators around the world besides Fermilab, of course. We already know about the Large Hadron Collider, LHC. Is it a circle or an n-sided polygon? It's kind of neither. The tunnel is a circle, but the way that the magnets are pieced together, you have to have magnets that help shape the beam, get it the right shape and stuff like that. And so it's kind of an n-sided polygon, but it's lots of n. And it's not a regular polygon either, because some lengths are longer than others. The magnets do have some curvature to them. So inside the magnet, it's not a perfectly straight bore. It actually winds around. So if I go to CERN, this is at the boundary between Geneva and France, like Switzerland and France. Let's open this up like this. Okay, here's the LHC Future Circular Collider, which is much bigger. Here's Geneva. Now this is looking to the southeast. Okay, so this is Lake Geneva right here. And the airport is right there. And the airport actually abuts the boundary between France and Switzerland. So Switzerland's right here, France is right here. Most of the Large Hadron Collider is actually in France. Okay, the campus where most of the scientific buildings are is right here in this area. And that's in Switzerland. But the border between Switzerland and France kind of runs along here. It cuts in. There's a really narrow arm of Switzerland that runs up this way and goes to the Geneva Observatory, where the exoplanet discoveries were at least built. They were made at a different institution or a different location, but they were built there, the instruments. But all of this part on this part of the LHC is in France. So there have been a series of particle accelerators at the LHC in the past. And that's the current iteration, the highest energy, but it had a series of other accelerators that were built at this location. But this is not all. So if you go to like DAISY, I think it's by Hamburg, DAISY, Deutschland Elektronen Synchrotronen something 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 or other. Okay, so this is a campus where they have another ring. It doesn't look like the ring is really visible. You can see some of these weird curved buildings. This XFEL, that's a free electron laser, X-ray free electron laser. What you get from taking charged particles that are moving really fast, and then you wiggle the electrons side to side, and that produces the synchrotron radiation. You can get beamed in a particular direction. Anyway, so DAISY is a similar type thing in Hamburg. Again, where they're trying to make electrons or like protons and antiprotons moving around and smashing into stuff. I don't know the design of DAISY very much because it kind of had been phased out by the time I got involved in this stuff. By the time I got involved in this stuff, SLAC had already wound itself down, and there was really only Fermilab and the Large Hadron Collider that were operating or even close to operating. There are also a variety of other locations. One that I can point to is Brookhaven. So that's the relativistic heavy ion collider at Brookhaven National Laboratory that's on Long Island. Okay, and it will have a familiar shape, a big circle in the ground. Okay, so here is the relativistic heavy ion collider. But you'll also notice there's other buildings that are circular in structure. Anyways, all of these things are designed to smash things together with high energies. Now, eventually what happened at Fermilab is they said, okay, we've done basically what we can do with fixed target experiments. We need to go to even higher energies, which means we want to have colliding beams. So for colliding beams, they needed to produce protons and antiprotons. So the protons they produce in the booster and they send around, in this case, clockwise. And the antiprotons, some of the particles that are produced here, they had a fixed target. They would hit the fixed target with the beam of protons coming out of the linear accelerator. That would produce some number, like 1 part in 10 to the 5, of antiprotons. And those were redirected into this area. This is the antiproton storage facility, something like that. So they would circulate around here, and then they would get injected going in the opposite direction. Okay, and what eventually happened was in order to get the highest energies that they could, I wonder, maybe there were actually colliding beam experiments done at Fermilab with electrons and protons. I'd have to go back and look at my history of the laboratory. They may have had some colliding beam experiments done in the main ring. I don't know how old this positron beam was. Either way, they could accelerate positrons going in the opposite directions. Positrons have exactly the same mass and exactly the opposite electric charge. So you can send them in the same beam, you can send them in the other direction, and you don't have to re-engineer anything. So I'll have to go back and look at my history of Fermilab to see if they did colliding beam experiments in the 70s and 80s. Either way, by the time the 90s came around, they had built this main injector. So this main injector right here takes the two beams, circulates them around, boosts them up to a higher energy, and then sends them into the main ring. But now they're going in at a higher energy. In order to keep those particles going in the right direction, steered, like curving at the right rate, they had to have higher power magnets. So the original main ring magnets at the Tevatron, or not at the Tevatron, but at the main ring, were conventional magnets. So they just run off of regular electricity. When they went to the higher energies, they had to have magnets that were like a factor of 5 in power, like 5 times the magnetic field. And the only way to do that was to have them supercooled. So they had to have superconducting magnets, because otherwise the beam was too fast and they couldn't steer them fast enough, or steer them along the beam using the magnets that they had, the conventional magnets that they had. So the Tevatron was a new ring that was built on top of the old ring. So when you go to Fermilab, they'll have, like, here's the old ring magnets on the top of these stands that went all the way around the main ring. The Tevatron magnets were placed underneath them, basically one on top of the other. Tevatron magnets, they were smaller in cross-section, but they were more, they were stronger magnets because they were superconducting magnets instead of conventional magnets. So they were they built these superconducting magnets. They needed liquid helium in order to cool them, and that's what these tanks do. So these tanks were filled with helium that they would compress to produce the coolant that would cool down the whole, I mean, it's 6 kilometers worth of magnetic field that they have in here. So there's like, yeah, so anyway, 6 kilometers worth of magnetic field that they have in here at 5 Tesla, which is pretty high. They have these, take the protons and antiprotons, put them in the main injector to boost it up in energy. Then it gets injected into the Tevatron, and then the Tevatron operated at a TeV. That's why it's called a Tevatron. It had 2 major detector facilities. It had the collider detector facility here, which is now called the Illinois Accelerator Research Center. When I was there when they had it as CDF and it was still operating. I was there when they shut it down. I was there when they replaced it with this building. And then that's when I left. And then D0 over here was another detector. Okay, so that's the Tevatron. In the Tevatron is where they discovered the the top quark, which was the last quark that was discovered. They kept operating the Tevatron up into the early 2000s, even to the late 2000s, near 2010. They basically eliminated all possible values for the Higgs mass. That was kind of the last particle that was discovered. It just turned out that the Higgs mass was in the worst possible place for their sensitivities. They were least sensitive at the place where the Higgs mass was actually located. The Large Hadron Collider took up the mantle and ultimately discovered the Higgs. Here they had, when you combined all the data that they took in the Higgs search, they had a 3 sigma detection. Like, it's not really a detection. It wouldn't be classified as a detection at only 3 sigma. But it was basically like a 99.99% chance that they had detected the Higgs. And that's not good enough in particle physics because you run a lot of experiments, and so you can have false positives. So after that, it was the Large Hadron Collider in Switzerland, where they were able to finally detect the Higgs with the confidence necessary to claim a detection. So they saw a hint of it at Fermilab, and the LHC ultimately took it over. One of the things that caused, or one of the differences between Fermilab and like the Tevatron and the Large Hadron Collider is that the Tevatron is a proton-antiproton collider. The LHC is a proton-proton collider. It's 2 counter-circulating beams of protons, and then they collide them together. The problem with beams of protons is that you can't have a single magnet. You can't have one magnet direct both beams. You have to have 2 magnets, or 2 different magnetic fields that are pointed in opposite directions, so that one beam gets steered clockwise and the other beam gets steered counterclockwise, because you can't rely on the fact that they have different electric charges to do that. And so when you look at the bore of the magnet for, so we'll go to CAST experiment. The CAST experiment, their image or their logo, do they have a logo? Do they show the logo here? Not seeing it. All right, well, that kind of ruined it. So, cast experiment logo. Yeah, here we go. So here's the cast experiment logo. The reason that I'm bringing up the logo is because it shows a cross-section of the magnets used in the Large Hadron Collider. Oh, that's not what I wanted it to do. Oh, they're looking for chameleons. How about that? Okay, so if you look at the cast experiment logo, it has these two eyeballs. Those are the two magnetic bores. So the magnets for the Large Hadron Collider has two bores, one with a magnetic field that points down and the other with a magnetic field that points up. And then when they want to collide the beams, then they just steer those two beams in towards each other. So they're moving in opposite directions, they steer them towards each other, and that's where they have the detectors. So that's why it has this particular shape, that's the bore. The Tevatron bore is just a single kind of square. It's not perfectly square, it's like a rounded square. Anyways, the point of all these experiments is to go and collide particles together, see what kinds of interactions take place. All right? And that was where these different particles were discovered and the particles that are exchanged between them. So, for example, that was where we discovered that quarks existed. We knew that as a consequence of these experiments that quarks existed. There are six quarks. Six quarks. Up, down, we've seen. Strange and charm, we've seen. And then the bottom and the top quark. Okay, they were originally called beauty and truth quarks, but that became a little silly, and so they're bottom and top. This was discovered, I think, in the 1980s, like 82 or something like that. This was discovered, I think, in 1995, and that was discovered at the Tevatron. The up and down quarks get most of their mass from the interactions of the gluons within them, and then as you move to these later generations of quarks, the top quark gets most of its mass from the mass of the quarks that make it up. The particles made out of the top quark get most of their mass from the top quark itself, where the particles made from the up and down quarks get most of their mass from the gluon field that binds everything together. So there are six quarks and six antiquarks. They couple to the strong nuclear force. Strong nuclear force is called the color force, or quantum chromodynamics is the study of the gluon field that interacts with them. So you'll have like an up quark and a down quark, and they will exchange gluons back and forth between each other, and that is how they couple together. They will come in either packets of three, so up, up, down, so that you can have a red, green, and blue color associated with each of those, and then it has no color. It's a colorless combination. Or you can have a quark-antiquark pair, something like this. This is a meson, so this is called a baryon. I'm sorry, not a baryon, it's called a hadron. No, it is called a baryon. Baryon. And this is called a meson. And both of them together, these are all called hadrons. So a hadron is a particle that's made out of quarks. You have baryons that are made out of three quarks, and you have mesons that are made out of two quarks. You can also have a recently discovered pentaquark, which is a quark, 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 antiquark combination. And you could have a heptaqark or something like that. You can imagine making other combinations so that ultimately it's a colorless quantity. So you have to have three that have red, green, and blue. These are like the equivalent of the positive and negative electric charge, except there's three of them. And then you have a quark-antiquark pair that would have to be the color and the anticolor. So this was discovered from the 1950s through the 1990s, is this ensemble of particles that make up matter. There are, along with six quarks, there are six leptons. The leptons are electron, the muon, and the tau, and then each one of these has a neutrino associated with it. Hold on a second, I gotta plug in. I'm about to lose my computer. So an anticolor would be like, okay, so you have electric charge, right? Electric charge is like a color. And then you have the anti-electric charge, which is the same color but the opposite sign. And so for the electromagnetic field, you have one charge, and that charge can have a positive or a negative sign. For the strong nuclear force, you have three different charges, and each one of those charges also has an opposite sign. And so they call it a color charge and an anticolor charge. Red, anti-red, green, anti-green, and blue, anti-blue. just like electric charge would be like electric charge and anti-charge, except that we just call it positive and negative because it's been around for a long time and that was the convention that we had. So fundamentally, with all these different experiments that came about, we had 6 quarks and 6 leptons. Okay, and the interactions between, so the quarks up, down, strange charm, bottom, top. The interactions between these things are, there's different kinds of interactions that can take place between leptons and quarks. Okay, the strong nuclear force, which is the gluon field, gluons, this is usually spelled with a G and not a Q, gluons. So this is the strong nuclear force. The gluons only couple to the quarks. Okay, so quarks experience the strong force. The quarks also have electric charge, so they experience the electromagnetic force and the strong force. They have mass, so they experience gravity. These actually are the particles that interact with all of the known forces of nature. There are 4 of them: gravity, electromagnetism, strong nuclear force, and the weak nuclear force. We're going to have to do the weak nuclear force next time, and go into a little bit more detail next time. So this is a bit longer of a discussion. The leptons themselves, these interact with gravity, electromagnetism. If they're electrically charged, they will interact with electromagnetism and the weak nuclear force, but they don't interact with the strong force. So no strong force. So the coupling between the quarks and the leptons only can take place through one of the other interactions, not through the strong force, but through gravity, which is extremely weak, so it's basically negligible, the electromagnetic force, and the weak nuclear force. As they interact with the electromagnetic force, that's how you get atoms. So the ratio of the strength of the electromagnetic force to the strong nuclear force gives you the ratio of the sizes of the nucleus and the atom. The atom is 100,000 times bigger than the nucleus. So, and the binding energy of the nucleus is roughly 100,000 times greater than the binding energy of, like the binding energy of the protons and the neutrons within the nucleus is roughly 100,000 times, it's like 1,000,000 times stronger than the binding energy between the nucleus and the electrons going around the nucleus. And that's why the sizes are different, right? If the electromagnetic force was stronger, then the electrons would orbit more close to the nucleus. And then there are a handful of interactions that can take place between the quarks and the leptons that's through the weak nuclear force. Weak force. F-O-R-C-E. And we'll talk about the weak force next time. Anyways, the strong nuclear force dictates the interactions of collections of up-down of these different quarks, and that's how you get the different particles in those particles that you can make from quarks. The 2 most important for us being the proton and the neutron. Okay, let me stop at this point and make sure, and then I will pick up next time with the weak nuclear force, because it's interesting in its own right. Let me take a look at the text and see what it is that I've covered and what it is that I might be missing. So we talked about pions. We've already talked about pions, how that's the thing that produces the force. I've already mentioned the fact that there are 4 forces in nature, that those forces come by the exchange of these different particles. This gluons, I don't think gluons are conjectured anymore. The graviton is conjectured. The photon and the W and Z, we'll talk about the weak force next time. Okay, and we've seen how these different, like I've done all these different kinds of diagrams before. Here is the cyclotron, I've mentioned that. Then these are the different rings that you have. Okay, shown, this is a breakdown of the tevatron, which I just described. Oh wow, I didn't realize that they injected into the main ring and then down into the tevatron. I'd have to see that that's actually, so they have a main injector. I didn't know that anyways, so looks like I don't know enough, everything that I thought I knew about Fermilab, but everything that I did tell you is correct. This is the one that I talked about at SLAC, at Stanford. And then the different conservation laws and so forth, which we've kind of described already. So we'll do the weak nuclear force next time. Does anybody have any questions?